Hi, good afternoon, everyone. So, this is the ninth week we are meeting for the course Fluid and Particle Mechanics. So, in this course, we so far talked about the governing equations of fluid flow. We derived the continuity equation, momentum equation, that is the Navier-Stokes equation, and then we talked about the dimensional analysis and scaling. So in this week we will talk about a very important topic which is very fundamental also. So we'll talk about the laminar and turbulent flow. Okay, so we'll give a qualitative definition of laminar and turbulent flow, and to some extent we will try to uh, see that how it is different from uh, like how the laminar flows are completely different from the turbulent flows. Okay, so laminar and turbulent flows. Okay, so let's, before going into the details of this, let's first calculate that what is the inertia force in a flow field. Okay, so the inertia force, like how the inertia force in a flow field scales. So the inertia force in a flow field Fi is equal to mass into acceleration. Simply, there is nothing difficult about that. So this mass is basically rho into some length scale q. Okay, and this acceleration is basically some velocity scale divided by velocity scale square divided by length scale. Now here this L equals to characteristic length scale of the flow. Okay, so L is the characteristic length scale of the problem. Rho is equals to density of the fluid. And this U is equal to characteristic velocity scale of the problem. Okay, so let's see that how this inertia force, so I'll call it as Fi. So Fi is actually proportional to this rho L cube into U square by L. So what is that? Is equal to rho L square U square. So I will call this as, I will now write the scaling in terms of scale. So I will write that this inertia force Fi scales as this rho L square U square. Okay, so I can write it in two notation. One is this, or I can write it as Fi is equal to, so I think this is fine. Okay, so far we got that this inertia force in a flow field scales as this. Okay, now let's see that how viscous force scales in a flow field. Okay, so the viscous force in a flow field F V, I'll call this as a B, is equal to what? A B is equals to mu U by L into L square. Okay, that means FV is proportional to mu UL. Fine. Okay, so I find that the inertia force scales as this and the viscous force scales as mu UL. Okay, where it is important to again note that this L is the characteristic length scale of the problem we are dealing with, U is the characteristic velocity scale of the problem, rho is the density of the fluid, and mu is the dynamic viscosity of the fluid. Now let's take the average between the two. Okay, so Fi divided by Fb is equal to, so what is Fi? Fi is rho L square U square divided by mu UL is the Fv. This is coming as rho L U divided by mu. Okay, we will call it as REL, that is the Reynolds number at when the characteristic length scale is L. That's why we are calling it as REL. Okay, so here is the important point. So what is the point? That we see that the inertia force in a flow field scales as this and the viscous force in a flow field scales as this, and the ratio between the two is basically a non-dimensional number, okay, which we are calling as the Reynolds number, okay, based on that length scale. So when Reynolds first identified this, he did the experiment, as we all know. So Reynolds identified that it is not the flow velocity or the length scale or the fluid properties that are important, but the collection of all these parameters, like in this case rho L U mu. So these collections of this parameter, which is important, and this collections of parameters is written in this form, is called the Reynolds number. So he did the experiment and he found that if I unaltered this term, this ratio, then the flow behavior is not changing dramatically or not changing at all. Okay, so the physical behavior of the system is dictated by this non-dimensional number called the Reynolds number. Okay, so Reynolds number is actually the inertia force divided by viscous force in a flow field. So this is important, and when, as I said, when Reynolds did this experiment, he also figured out that somehow there is like there there exists a critical value of this Reynolds number, again that uh, based on the problem. Let's say for a pipe flow problem, the critical Reynolds number. So now I will come to the definition of the critical Reynolds number. So the Re critical, RECR, let's say, is equal to rho some average velocity u, some characteristics length scale u divided by mu. So in case of, so I am defining this in case of a pipe flow where rho is the density of the fluid, u is the average velocity of the fluid, and d is the diameter of the fluid. Okay, and the critical Reynolds number. So the critical Reynolds number for flow through a circular pipe is about 2300. Okay, but it is important to know the significance of this critical Reynolds number. So for the case of a pipe flow, the critical Reynolds number is (2300). For a different flow situation, let's say for the flow through a channel or some open channel flow or some atmospheric flow or in any other flow problems, it may be different. Okay, so he also identified that there exist. So when Reynolds did the experiment, he also identified that there also a value of this non-dimensional quantity below which the flow is always a regular orderly flow, but once he exceeds this Reynolds number, the flow become disordered and chaotic random flow. So the significance of the critical Reynolds number is that the critical Reynolds number doesn't mean that the Reynolds number beyond which the flow is turbulent, but it defines the other way around. It says that the Reynolds number below which the flow is always laminar is called the critical Reynolds number. So in a physical sense, what happens is that, let's say you are doing an experiment, and when you do some experiment, there are always some unwanted disturbance or the perturbations from the surrounding, and if in that experiment you are doing, your Reynolds number is less than the critical Reynolds number, then all these perturbations or the disturbance get absorbed, and the these disturbances will not be amplified. Okay, and these disturbances will not be amplified if the flow is a laminar flow, or rather the Reynolds number is less than the critical Reynolds number. But if it is a turbulent flow, rather if it is a apparently disordered motion of the fluid, then if you give any small disturbance or if you perturb the flow slightly, it will become turbulent, because that small perturbations will be amplified, okay, because of the inertia force present in the flow. So for a turbulent flow, the it is the fluid inertia that actually amplify the small perturbations, and that that perturbations will never die out in case of a turbulent flow, but in case of a laminar flow, okay, then these perturbations will get absorbed in the flow field, and it will not amplify. So that is the importance of critical Reynolds number that you need to remember. So it is not just a number, it has the significance, and the significance is that below this number, if in my experiment my Reynolds number is less than the critical Reynolds number, then if I give any disturbance, irrespective of the amplitude of the disturbance, it will get absorbed and it will not amplify, and with time it will die down. But if in my experiments the Reynolds number is more than the critical Reynolds number, then this disturbance will eventually get amplified, okay, and the flow will be more and more random and chaotic, okay. So this is the significance of the critical Reynolds number that we need to remember. And so if I write it in that sense, so this laminar flow laminar flow is a regular orderly motion of fluid elements. Okay. The turbulent flow, on the other case, have many characteristics, in fact. So let me write down the sum of the characteristics we know. Okay. So the first one is that there is a randomness in the velocity with respect to time, because the velocity is not a steady velocity, okay, or velocity is not regular orderly, it has some fluctuations, okay. So that I am saying that there is a randomness in the velocity with respect to time. So let me write it down. There is a randomness of the velocity field. I will call it as u vector, okay, with respect to time. Fine. The second one is the velocity is also disordered with respect to space, okay. Okay, so that means the velocity fluctuates both with respect to time and the spatial coordinates. Okay, that means there is a random fluctuations in the flow field with respect to both time and space. This is the first characteristics of the turbulent flow. There is a wide range of length scale and time scale over which these activities are going on. Okay, so wide range of, we will discuss about this length scales in detail shortly, that like what are the different length scale which are present in a turbulent flow. Okay, so these characteristics is the wide range of time scales and length scales over which the activities are going on. Number 3, the fluid motion is chaotic. Now, the definition of a chaos is something different. I will not go into the definition of it, but just in a literal sense, what you mean by chaos, you can think it in that sense only. Okay, so the motion is chaotic, and in turbulent flow the mixing and diffusion which takes place is usually more than in case of a laminar flow. So that I will call as enhanced mixing and diffusion. Okay, so far I discussed only about the scaling of the inertia force in a flow field, the scaling of the viscous force in a flow field, and Reynolds figure out that the ratio between the two, the inertia force by the viscous force, that actually dictates the behavior of the flow. Okay, and then he defined the Reynolds number, and he also figured out that there is a critical value of this Reynolds number depending on the flow situations, or depending on the problem, below which the flow is always laminar irrespective of the level of disturbance or the perturbations you are giving, but beyond which the flow is always turbulent. But the definition of the critical Reynolds number is not the latter one, okay, the former one. And then, as we all know, that the critical Reynolds number in case of a pipe flow is around 2300. So beyond this Reynolds number, the flow is transition and then turbulent, but the below which it is always laminar. Then we can formally qualitatively define, okay, what is the laminar flow and what is the turbulent flow. So as you can see that the laminar flow is a regular orderly motion of the fluid elements, whereas in the turbulent flow there are lot of time scales and the length scale presence in the problem. There is a randomness or the random fluctuations both with respect to the time and space. Then of course the motion is chaotic, and there is enhanced diffusions and mixing. So because of that, let's first give a like physical sense that like what turbulence do. So we all know, as we are talking, as we are mentioned the critical Reynolds number in case of a flow through circular pipe. So let me draw the velocity profile for the two cases where there is laminar pipe flow and there is turbulent pipe flow. Okay, so let me draw it. So I will have laminar pipe flow, and then I will tell you the significance of the velocity profile, like what turbulence do. And I will write it as so. As you know, in case of a fully developed laminar, of course both of them are fully developed I am talking about. So in case of a fully developed laminar pipe flow, so how is the velocity profile? It is a parabolic velocity profile, right? It's a nice parabolic velocity profile, as you all know. Okay, so in case of a fully developed so this is the velocity profile for a fully developed laminar flow where the velocity is more at the center line and it decreases as we go along the walls of the pipe, and it becomes zero at the wall of the pipe if we apply the no slip boundary conditions, and it's a nice parabola, as you can see the velocity profile. Okay, but the velocity profile in case of a turbulent flow, the average velocity profile if we talk about, so it is something like this. Okay, so let me draw it little nicely. So it will be something like this. Fine. So what it will be, how it will look like? So it is almost, it is a straight line at the center. Towards the center line, it's almost a straight line, and as we go near the wall, the slope is actually here. So it's less gradient in this case. So this is my turbulent laminar velocity profile, which is a nice parabola which we can calculate, where we can calculate the velocity profile analytically, in fact by solving the Navier-Stokes equation in this case. And this is a turbulent velocity profile, the average velocity profile. Okay, the original velocity profile might be something like this, that there will be fluctuations over and above this rate line, but we are not going into that details of that case. Okay, so the turbulent velocity profile is more and more uniform on an average, and this uniformity has come from very good mixing of different fluid layers. So uniformity is more when we have less gradients, and more mixing ensures that there is less gradient. Okay. So these things we have to remember, that the calculation of the velocity profile in case of fully developed turbulent flow is not that easy, but in case of fully developed laminar flow we can analytically do that, but qualitatively we can say what are the differences. Okay. So the qualitatively, as I said, that it is more and more uniform, at least at the near the center of the pipe, near the center line of the pipe, and it is and this uniformity has come from the oil mixing. Okay. And the oil mixing actually ensures the less gradient. So I will not go into the details of all these things. This is just for your understanding, like the qualitative understanding, as I can say. So that's the basic difference between the laminar and the turbulent flow. Okay. So okay, so now before going into the statistical characteristics of the turbulence, we will try to understand that what are the instrumentalists who play a big role in sustaining and creating the turbulence. Okay. To do so, we will look into this from a different perspective, and we will see that we can explain it quite well through an important concept called eddies. Okay. So eddies are basically strongly rotating structures of fluid lumps. Okay. And the interesting questions is that what are the size of these eddies. Okay. So we can have small eddies, we can have large eddies. The large eddy can be as large as the characteristics length scale of the problem, and the small eddy is maybe as small as something called the Kolmogorov length scale that we will see in this class. So the important concept here is that we can qualitatively explain that why like explain the reason behind sustaining and creating turbulence, and these eddies play an important role. Okay. So let me write it in a statistical sense, that I can always write the velocity profile in case of a turbulent flow as the sum of two velocity. One is the average velocity. So this is the average velocity of u, and there is some sort of fluctuations. Okay. So let me write it in. So this is the average velocity and this is the fluctuations. So I will call it as, this is mean, and this is fluctuation. So you can always decompose the velocity profile in this way. Okay. That there is a average velocity or the mean velocity, and there is fluctuations of the fluctuations over and above of this average. Okay. So as I said, that the interesting questions here is the length scales of these eddies. Okay. So the eddies are the fluid lumps of strongly rotating structure. So one can explain it through a concept called turbulent energy cascade. Okay. So I'll just revisit it very shortly, and I'll discuss that how these energy cascades actually can explain behind the explain nicely that what are the different length scales present in the problem, particularly the large length scale, the large eddy length scale, and the small eddy length scale. Okay. So as I said, there is this random fluctuations, and these random fluctuations are there because of the disturbance in the flow. Okay. So the disturbance in the flow may be instigated by the roughness element of the wall, or maybe slight change in the initial conditions of, in case of a flow through a pipe. Okay. And these fluctuations create a rotating structures or these eddies. Okay. So the large eddy can have a length scale which is of the order of system length scale, and the small eddy can have the length scale which is of the molecular level also. Okay. But we will define that the length scale of the small eddy is something called as the Kolmogorov length scale. Okay. So what happens is that the large eddy extract kinetic energy from the mean flow and dissipate it to the smaller eddies, and these smaller eddies again dissipate the energy to the smaller and smaller eddies. Okay. So there is large eddy whose length scale is as large as the system length scale. It extract the kinetic energy from the mean flow, dissipate it to the eddies of smaller size, and these smaller size eddies again dissipate it through the smaller eddies, and it's go on. But where it will stop? So for these large eddies, the inertia forces dominate. Okay. For the smaller and smaller eddies, for the very small eddies, the viscous force dominate. Okay. So you have the large eddy where the inertia force govern the dynamics. You have the small eddies where the viscous force govern the dynamics. So let me write it down in case of in form of an energy cascade, then it will be clear, I guess. So So we have the mean flow, which is this U bar. It extracts the kinetic energy. So large eddies extract the kinetic energy from the mean flow. It dissipate it to the smaller eddies, and then it's again dissipated in smaller and smaller eddies. And it goes on. Okay. But the important question is where it will stop. As I said, here the inertia force is important here for the small steady. Here the viscous force is important for the small eddies. Okay, for the large eddies the inertia force is important, for the small eddies the viscous force is important. And there is a continuous flow of energy from the large eddy to the small eddy. The small eddy will finally dissipate the energy through the viscous dissipation. Okay, and this, like here, as per the Kolmogorov's, to derive the Kolmogorov length scale, we will say that the smallest eddy, let's say for the smallest eddy, the Reynolds number based on the smallest eddies, let's say the length scales of the smallest eddy is eta, then the Reynolds number based on the small scales is order 1. Okay, so Reynolds number is order 1 means what? The inertia force and the viscous force are of the same order. Okay, so let me see. So the small eddy, as I said, that dissipate the cascaded energy through the viscous dissipation. So let me, before deriving that, let me make a table of, let's say I am talking about largest eddy and smallest eddy. Okay, so L is the length scale, U0 is the velocity scale, T is the time scale. For the smallest eddy, let's say eta is the length scale, V, small v is the velocity scale, and T prime is equal to time scale. Let's say the pi is equal to the rate of extraction of kinetic energy from the mean flow in case of large eddy. Okay, so I'll just write it down, and this epsilon is the rate of dissipation of the cascaded energy through viscous dissipation. Okay, so eta, so L is the largest eddy length scale and eta is the smallest eddy length scale. Okay, so this rate of extraction of kinetic energy from the mean flow through the fluctuations pi, that scales as u0 square by t. Okay, where u is the characteristic velocity scale of fluctuations in the largest eddy and t is the time scale, which we call as the uh, typical turnover time scale, large eddy turnover time scale. Okay, so this large eddy turnover time scale is the characteristic time scale that the large eddy takes to be energized by extracting the energy from the mean flow. Okay, and what is T in this case? The time scale. So the time scale T is also length scale by velocity scale. So what is pi? So pi is coming as u naught cube by L. So that means the rate at which the large eddy extract the kinetic energy from the mean flow, that is pi, scales as u naught cube by L. It is important. Okay, and for Re to be 1, and ultimately all this extracted energy will be dissipated through the small eddy. So the dissipation length scale so the dissipation rate for the small eddy will also be u naught cube by L, because it goes from ultimately this is extraction to dissipation. How much it will extract, how much large eddy will extract, it will dissipate through viscous dissipation through the small eddies. Okay, so the large eddy will extract the kinetic energy from the mean flow. It will transfer it to the smaller and smaller eddies, and these smaller eddies will dissipate this extracted kinetic energy through viscous dissipation. Okay, so this is how you can scale it. Now the viscous dissipation, okay, the rate of dissipation at the smallest eddy scale per unit mass, the rate of dissipation at the smallest eddy scale, of course per unit mass, epsilon scales as nu v square by eta square. That is the viscous force, as simple as that. Okay, that is the viscous force terms in the Navier-Stokes equation. Is that fine? Yeah, where nu is the kinematic viscosity of the flow, and this v is the smallest eddy velocity scale, and this eta is the smallest eddy length scale. Fine. What is Re eta as per the definition? Re eta is order 1. Okay, so that means what is the definition of Re eta? It is v eta divided by nu is order 1. Okay, that means your v is order nu by eta, as simple as that. So what is epsilon? If your v is nu by eta, so epsilon scales as nu 1 by eta square into v square equals to nu square by eta square. Okay, so that means your epsilon scales as nu cube, yeah, so it is nu cube by eta to the power 4. Is that right? Yes. So that means what is eta? So eta to the power 4 scales as nu cube by epsilon. That means eta scales as nu cube by epsilon the whole raised to 1/4. This is called the Kolmogorov length scale. So the Kolmogorov length scale scales as nu cube by epsilon the whole to the power 1/4. This is called the Kolmogorov length scale or the smallest eddy length scale in this case. Okay, so this is how you can see that how eta is defined. Now as I said, so now I can put the value of epsilon in this, because the epsilon is again u naught cube by L, right? So let me put it that. So my eta scales as, so eta to the power 4 scales as nu cube by epsilon. That means eta to the power 4 scales as nu cube. What is the epsilon? Epsilon is u naught cube by L. Okay, so u naught cube by L, that means L will be of u naught cube. Am I right in this? Yeah. So I can write in this form that eta to the power 4 divided by, let's say, L to the power 4 will be scales as nu cube divided by u naught cube into L cube. Am I right? Yes. What is this? This nu cube. So REL is it, that is the Reynolds number based on the large eddy length scale, is u naught L by nu. So this actually is equal to, this actually is equal to 1 by REL cube am I right? Okay, so that means your eta by L scales as REL to the power minus 3 by 4. Okay, or you can write that eta scales as L into REL to the power minus 3 by 4. So that means if you know the large eddy Reynolds number and the large eddy length scale, you can at least get a sense that how the smallest eddy or the Kolmogorov length scale is. Okay, so this is an important thing. Now to get a sense like how you like how these scales are, to get a physical sense. Okay, so let's say I have a flow. So let's say my L, that's large eddy length scale, is of the order of 1 meter, and I have REL is typically of the order of 10 raised to 4, which is very high. That means the turbulent flow. That means what is the value of eta? Eta is of the order of 10 raised to minus 3 meter, or of the order of 1 millimeter. So you can see the difference in scale. The large eddy, if I consider the Reynolds number is of the order of 10 to the power 4, if my large eddy has the Reynolds number of if my large eddy has the Reynolds number of 10 to the power 4 and the large eddy length scale is 1 meter, then the smallest eddy, or the Kolmogorov length scale, is of the order of 1 millimeter. So you can see the difference in the length scale. Anyway, so we'll stop it here, and in the next class we'll talk about the statistical description of the turbulent flow, and then the I'll go into the Reynolds averaging Navier-Stokes equations, or like the averaged equations, and the Reynolds stress, and then we will solve the assignment problems. Okay.